Hey everyone and welcome back. We are now going to do our full Quicksort Java implementation. We're just going to use a basic array for right now, but you could use an array list as well. Anything with random access would totally work. We're going to use our Lomuto partition, which we did go over in the previous video. And we're going to see the smallest possible sort of correct version of this code. We'll trace it through, and then, yeah, if you want to try and implement it with like an array list instead, that's always a really good challenge. We're going to build a bunch of helper functions to sort of help us get all the pieces we need in place to make this work. To start off, since we already understand partitioning from the previous video, it's important for us to understand the basic structure of Quicksort. I'm just going to put it in a comment here, actually. I'm going to have a base case, partition, and two recursive calls, left and right. So hopefully this reminds you a little bit of what we had for merge sort, where we had our two recursive calls. Rather than a partition, we had a merge function, and our base case was the same, actually. So that's nice and easy. I'm going to be using the exact same values or variable names that I used before. Low, high, boundary marker, pivot, value. Actually, they will not be exactly. I want to be able to be a bit more specific here. Low index, high index, boundary index, pivot value, and scan index. Just so we can have a better understanding of where we're keeping track of a value versus where we're keeping track of a index. Okay. So what is it that we're saying when we say base case, partition, and then two recursive calls? Well, we're saying if our low index somehow ends up higher than or equal to our high index, we need to break out, stop, recursion, return, whatever, right? We need to get out of there. That's our base case. We then have our partition, which I did describe in the previous example. In the previous example, I described the partition. Then what do we mean by partition? Well, we're going to go and run our partition algorithm, and that function typically, will return the boundary index. So we can run our partition function, and then at that point in time, given that we have our boundary index and our mutated array, we can now go ahead and make those two recursive calls to the left side from low to boundary index, already dropping the word index everywhere, and then the right side, I wrote size, side, and the right side from the boundary index +1 up to our high index, and so on and so forth. So there are a few moving pieces here. Let's just break it down before we sort of put everything all together here. I think it's really important that when we're doing modular code writing, that we're actually being very careful in our implementation, which means I'm going to start with my array here, new int array, and I'm just going to put values in it that we used in the previous video as well. So we had 8, we had, trying to remember, 3, 1, I think. We had 7, we had 0, we had 10, and we had 2. There we go. Okay. And it's always good for us to just make ourselves a print function just in case we need it. I'll go ahead and write one up very, very quickly. Public static void print, just so that if we're running through our code, it's really easy for us to see what is going on. For each in I in A, and we'll just do a print of that value with a space, and then at the end we'll just do an extra print line. We can just test this really quickly to make sure that even like our most basic stuff is set up in a way that isn't gonna like break our code. We need this to be working for other things to be working. Let's just make sure that worked as I'd expected. Okay. With that in mind, let's get into some real code. We're going to start by writing a swap helper. If you remember from the previous video, I mentioned as part of the partition, we have to be able to swap. So our public static void swap function is imperative. We can give it the first index that we want to swap, the second index that we want to swap, and we can give it the array that we are doing this swap in. Now, if you're new to swaps, go back and look at exactly what we did for selection sort, because you shouldn't be. This is very, very standard at this point for us. We have a temporary variable where we take I at index 1 and store it. Whoops. There we go. We can then go and overwrite whatever's in I of index 1 with whatever's in index 2. And then we can overwrite whatever's in index 2 with that temp. Now, I'm not handling any like index out of bounds issues, etc. But for now, we're going to assume that our code is going to work as intended with the values intended. Now, I still, like I said, believe it's important for us to test this. So let's go ahead and call that swap function up here. And let's swap position 0 and position 2, just to make sure that it works. 0, 2 with A. Now, I'm going to print it again. And I should, before I print it, write down what I'm expecting to print out. This is going to help me solidify my own understanding of the code, and it's going to help make sure that I'm not like getting swayed or biased when I see the output. Based on my understanding, 1 and 3, position 0 and 2, so values 8 and 1 should swap positions and nothing else should change. So these are my expected outputs. I'll go ahead and I'll run it. And based on my output, that's exactly what I got. It's exactly what I expected. I'm feeling really good about that. So I would say at this point, my swap is written and complete. I'm just going to collapse it now. All right, now that we have the swap, we can actually write our partition code because we needed the swap in order to do that. Static int partition. Now, what is this going to take in? It's going to take in our int array A. It will also take in the low and the high position, because our boundaries in our array might shift as our piles become smaller and we kind of get into those subset piles. Now, what that means is that those variables that I was previously mentioning, like the like low and high, those have to be set elsewhere. So for right now, this returns the boundary marker, the boundary index, and for now, low is 0, high is a.length minus 1. Okay, that should work. All right, so now inside the partition, what is it that we actually need access to? Well, we're going to need that pivot value. And our pivot value is going to be equal to a at high. We know that this is not going to fall off the array because I'm telling you as a precondition that high is set to an indexable value. It's going to actually be .length minus 1. So we know that that will work. We also need that boundary index that we're going to keep track of. And like we said in the previous video, it should be starting at low in this case. Well, starting at 0, but in this instance, that's the same as low. We want it to be tied to low. This pivot value and boundary index need to be relative to high and low for this to work appropriately. So don't hardcode in a.length, don't hardcode in a 0. These need to be made relative to the information we have available to us inside this partition. Now we can run our loop just as we had written up in the previous video, where we're going to go for each of those indices. I had called it like a scan pointer, J, whatever it may be, and it's going to start at low. And we're going to go up to, but not including high. And a reminder that that's acceptable because high here is going to be our pivot. It's our pivot. We don't need to actually run this loop on our pivot. Oops, index, and then index plus plus. There we go. And as I said, if our array at our index is less than our pivot, we have work to do. We need to do that swap. And what did we say about the swap? Where is it? Right here. Index 1, index 2, and A. And in my previous video, I told you that we're going to be swapping index 1 being our boundary index. And we're swapping it with the index from our loop. There we go. And once that's done, we also increment our boundary index so that next time we're moving along our array appropriately and keeping that in place. And then the last thing I said in the previous video is not to forget to swap your pivot into the right spot at the end of this. So how are we going to do that? We take our boundary index, we take our high value, and we swap them. So now we move our pivot into place. Once we've done all that, we can return our boundary index, and this is now in the right position. If you want to see this sort of code traced out instead, go back to my previous video where I do walk through the partition code. But that's it. That's our whole partition. It looks exactly the same as I had in the previous video. Once this is finished, we can understand that everything before that boundary index is going to be less than pivot, that our index right here in our for loop is our scanning variable, that we have our final swap occurring to place our pivot in the right spot, and we can return I so that when we get to the recursive part in just a minute, we're able to split around our boundary. Actually, before we move on, I'm going to test this code because I told you I was totally going to do that. We've already tested the swap. I'm going to remove this just for now. But what I will do is I will get that int p equal to partition. I'm going to pass in a. I'm going to send in my low as 0. I'm going to send in my high as my length minus 1. And then based on my own understanding of the Lomuto partition and the code that I wrote, I am hoping that we get a partition, a boundary index of whatever that p is that comes out, and then I can print it out as well. So if I look at my array, I should understand that the pivot is going to be chosen to be 2, this value, and after everything is done, as we saw in the previous video, this 2 should end up in index 2. So this should print out index 2. And with that in mind, we also should be able to understand what this is going to print out. And again, you can go back and look at my tracing video, or you can just take a minute and trace it yourself right now. It won't take you very long, but this should give us something like this, where everything to the left of 2 is less than 2, and everything to the right of it is going to be greater. Whoops. So let's just give this a quick run and make sure that the partition code that I wrote is correct. And look at that, I've already got an error in my code because I called it pivot value here, but I only called it pivot there. So this is why we do these tests. Better to figure them out now. All right, let's try again. There we go. Now it compiles. When we run it, I'm just going to quickly compare. My index did indeed come out as 2 as I expected, and then 102, 73, 10, 8, 102, 73, 10, 8. I got the exact output that I expected based on my understanding of my partition method, so I implemented it correctly. Now we can move on to the actual official Quicksort. So now I can collapse this and we'll go from there. All right, let's add in that method header. Public static int, void, pardon me, quicksort. We're going to pass in our array A, we're going to pass in that low, we're going to pass in that high. Now, how are we going to do this? Well, let's take a look here. What did we exactly say our quicksort was broken into? Base case, partition, our 2 recursive calls. I labeled out all the different values that we were probably going to use, and then I took that base case, partition, 2 recursive calls, and I broke it up even further. So why don't I pick up those 4 comments and pop them into my quicksort method. There we go. And we're just going to turn each of those comments into code. It's one of the easiest ways to go from words to code. Now, as you know, I don't love empty return statements. So rather than an empty return statement or like an empty if statement, I am going to flip this to say if my low index is less than my high index. So I negated it. And then I'm just going to put everything in here inside this nested if statement. That's a better programming practice, certainly for this course, but also just in life. It's very clear to say basically, if this is true, let's do the work. It's always nice to sort of assume innocence until proven otherwise. So what is it that we're going to do? Well, we have our int A, our low, and our high. So let's first call our partition just like we said we would. This becomes int boundary index equals partition. And what does partition take in? Right here, A, low, and high, and those are coming in directly from the quicksort, so no problem. A, low, and high. I'm just passing those straight through. After that's completed, we need to be calling our left side partition now. And this needs to not include the actual boundary index, since we've already established that our boundary index is in the correct position. We don't want it to be reprocessed. So what that means is we can now call Quicksort, which has these three parameters on A, with our low index being the same, but now our boundary index has shifted our high over so that we can only concentrate on the left side of the boundary index. And then once that one is done, we can do the exact same thing to the right side. This one starts at boundary index +1 and it goes up to our high index. And believe it or not, that's all there is to it. We're done. That is our Quicksort. Now we've tested our print, we've tested our swap, and we've tested our partition. Let's go ahead and test our Quicksort. Quicksort, we're going to pass an A. We understand that the top position low is 0. The top position high should be our last element. And once it's all said and done, we should end up with an array 0, 1, 2, 3, 7, 8, and 10 in that order. So in our ascending expected order. Moment of truth, right? Let's go ahead and run this. Oh, everywhere I put just high, and now suddenly I've decided to change it to, I'm just messing with myself at this point. Not intentionally either, which I can't decide if that's better or not. Here we go. High index. It's a good thing that we've been testing as we go, because then I can catch all those little mistakes when there are only a few at a time, because I make a lot of them. Okay, so we ran our code, and what we can see happening is that we do actually get exactly what we expected. We have our initial array being what we expected it to be, and our final array being all ascending. A lot of magic might have just happened behind your brain. So something you can always do is you can add in the print statements inside Quicksort as well, so that you can print at each stage if that is something that might help you. So for example, we can run this again. You can add other little enhancements along the way, but what you can see here is our original, then the 2 was put in the right spot, then the 1 was put in the right spot, then the 0 was put in the right spot. Then on the other side, our 8 was probably put in the right spot. Is that this one? Yeah. And our 7 is put in the right spot, and then our 10, and we're all done. So we can actually sort of see what's happening a little bit better if we print as we partition as well. That's always an option. Now, some of the most common pitfalls that we run into are things like this right here, causing infinite recursion. If we swapped this, but forgot to swap our sign, we could end up in a situation where we have infinite recursion or things don't work as expected. Same thing with our recursion ranges. So making sure you have that -1 and +1 so that we eventually do reach a place where we can say that low is no longer less than high. If you mess these up, it's possible that you'll never reach a base case. And of course, you need to make sure that we don't forget in our partition to actually swap that pivot into the right spot and then return that boundaries index so that we know where we need to sort of split our two subgroups up for the next round of this code. If you want an array list version, I think it's a really great exercise because the swaps can sometimes be really annoying with an array list, depending on how careful you're being or not. So feel free to try to implement that yourself. But that is the whole algorithm. That's it. It's really not that bad when we break it down into these pieces. Next, we're going to actually see how pivot choices might change the amount of work that we do and the analysis around this sorting algorithm, as well as how it compares to the other sorting algorithms that we have seen in this course. Thanks, everybody, and I'll see you in our final video all about analyzing Quicksort. Thanks. Bye.